Parada.
I'm Farhan Amin.
I'm Linnea Krall.
Tommaso.
And we're the team Mary Cariola. So Mary Cariola is a local school here in Rochester that serves students with physical and developmental disabilities. So our goal here is to make a drawing device with a 2D translation stage, and it's going to be powered by buttons that are accessible to the children. Yep, like I said, not all students are able to hold the writing utensils in their hand. So we want to do something that allows them to color pictures on paper with markers and crayons that they can then take home. So we've got some requirements. The device needs to be transportable and able to be angled so that students can have it raised so they can see it better. It needs to be compatible with the provided buttons, like I mentioned, and also most standard writing utensils so the students can choose what they want to use. It needs to be child-proof, so it's going to include a safety cover so that there's no pinching or injury from the moving mechanism. It needs to be easy to replace the paper so a teacher can put in fresh sheets for different children, and it's supposed to be non-digital, so it's all paper, no screen.
So along with our problem definition and our requirements, we also have some specifications. And the specifications are as follows. The max paper width and height have to be 24 and 18 inches respectively. And the base thickness is a max of 1/8 inch, an eighth of an inch. And the max weight we set for the device was 20 pounds force. And then we also want the device to be able to be usable like on an angle. So the max angle that we want the device to be able to be operated at is 45 degrees. And then we also have some motor torque, which is 4.4 pounds force per inch, and then power supply of a max voltage of 5 volts.
So for our concept, as Linnea said, we have a translation stage, and so what we use to make the two rails that are going to be translating along the base are 80/20 rails. In addition, attached to the rails are sliding carts, so this rail over here that translates along that one, there's a cart attached to it so that it can move across that rail. And then there's also custom brackets and mounts that we manufactured ourselves, and also pulleys, belts, and limit switches, which we got.
To constrain the pen to the translation stage, we designed a pen holder. The pen holder is able to be used on different writing utensils. So it's a spring arm that'll open up and then come down onto the utensil to constrain it against. There's a back plate on it. Some of the material is 3D printed, some of it was metal. And yeah, we have these L slots, as you might see in the middle, and that allows the pen to account for any changes in the base thickness, so because it's not going to be completely level.
So then, as I mentioned, we needed that safety cover, so that's this design you see here. So it was going to be a flat rectangular base with the removable cover, and there's a sliding lid. So we've got small stoppers to keep the lid from moving too far off the base. 3 of the sides are going to be wooden, and the front side and the top are going to be clear polycarbonate for the children to be able to view their drawings.
And then as well with all 3 of these, we also need some coding, and that was my job. And so the basic logic of the code is as follows. It's anytime a button is pressed, the motor will change directions. Anytime the limit switch is hit, the motor or the code tells the motors to then move backwards and then just stop for like a couple seconds. And then there's also a potentiometer that will adjust the speed based off the potentiometer's value.
So here's a little bit of analysis we have to do throughout. In the left-hand side of the screen, we have our spring arm FEA. So the spring arm's the mechanism coming and clamping down on the utensil. So simulated, we had a force going through the middle of about 2 pounds, which would be about the max we were looking at from the spring. The max stress was fairly low, and the deflection was about times 10 to the -5th of an inch, so very small. So we didn't expect any issues there. That passed the analysis there. We also tried it with our initial, since the deflection was so low, we thought maybe we could 3D print it. We 3D printed that, it snapped, so we decided to go with aluminum for that.
So on the bottom left here is a fastener torque calculation. So this is a calculation to determine the torque necessary for a 632 bolt and its fastener. So it was determined that the torque was about like 12.4 pound-force inch, and that just goes to show how it wasn't necessary to use a larger size screw, since the screw was used to fasten a belt to one of the carts that we had. And then towards the right on the bottom, there's a cantilever beam analysis, and basically at the end there's a 1 pound force. And so earlier in the design stage we were debating on whether it was necessary to have a ball transfer at the end of the rail to keep the beam balanced, but based on this analysis there is a max deflection. Even though it's somewhat small, the ball transfer allows the beam to not bend, so we decided to keep it. Okay, so in terms of some of the stuff that we manufactured ourselves instead of bought online, so we have a lot of different mounts that we made and also brackets. So the first one is a pulley mount. These are just mounts that are able to connect the pulleys to shafts so that the belt can go around the motor shaft. We also have limit switch mounts. These are just little brackets or plates that we made that connect to the 80/20 and allow the limit switches to be mounted so that when the cart hits it, the code will tell the machine to stop. We also have motor mounts. These are just so that the motor can lay on its face and be attached to the rail. And then we also have a slide bracket, which these are so that we can connect the belts to the cart.
As for the pen holder assembly, there were 5 major pieces to that. Backplate, 2 arms, a V, and a stopper. Everything but the V was manufactured on a mill, either by us or by Bill Meldenberger over in Taylor. The V, we decided to go with a 3D print. There wasn't a very high stress through that, and it was a bit of a complicated shape, and we went through a few trials for it, so it was best to go with the 3D print for that, and then fasten it to backplate.
So the base was also manufactured by us, since it's just a piece of plywood, so we were able to use the table saw to cut that rectangle, as well as to cut the small stoppers, some sanding to keep those edges from being too sharp, and hot gluing the stoppers to the base. The safety cover was mostly made by Bill with polycarbonate plywood. We had to change the design because the height was a little too low, so we added an inch strip of wood on the base, and then we popped out the front wooden panel and replaced it with the clear polycarbonate to increase the visibility.
Here are just some pics from manufacturing. Pen holder, that's the first prototype and the second prototype coming off the 3D printer, and then down at the bottom is the final pen holder assembly.
And then here we have, this is the base with the cover minus the lid, and then here we have the lid where you can see there's this small groove that's gonna let it slide in and out.
So here we have some of the circuitry. You can see the Arduino and the motor shield, the Adafruit motor shield up here. So yeah, up there's a picture of us just soldering some wires together, and we had to use the soldering iron and the hot air gun to put some just a heat seal it on top there. And then we also have some assembly photos as well of mine.
Yeah, so as I mentioned before, some of the stuff we manufactured are imaged here. So we have on this bottom left side the motor mount, so you can see that the shaft is kind of coming through the bracket so that it can have the pulley attached to the other side so that the belts can wrap around the rail. And then more on the right, There is the limit switch mount, which we made so that we could attach it to the rail. And so the cart is like imaged right next to it, and that's the pen holder cart. So when it is moved by the motors, it'll hit the end of the limit switch and then it'll stop.
So here's the result of some of our testing. We tested the specs for the paper widths and height. We were a little bit off. Our sponsors just said kind of 24 to 18 inches for the max size of paper he'd use. He didn't seem to be that upset when we said it might be a tiny bit shorter. The base thickness, that was kind of just a value we had chosen at the beginning, and then that was before we decided to go with plywood, so they don't make 1/8 inch plywood and it wouldn't be very sturdy. So we wound up with the 1/2 inch, and that's what was available to us down in Retner. The max weight, we went a little bit over. I think that also accounts for we switched the safety cover to wood instead of all the acrylic, and then the base obviously is 4 times as thick as we had originally planned. And then the tilt angle range from 0 to at least 45 degrees, we passed that. We measured that with a tilt test. We tilted the box up until the cover slid out, and then measured the height, did a little sine calculation, and then found out what that degree was. It was about 70 degrees. We did it a couple times.
So to conclude, and in terms of future work, with more time on this project, the next steps would probably be to make the assembly quieter and maybe brush up on some parts in manufacturing. And yeah, especially because the device is meant to serve children with sensory issues and sensory needs. A loud device is not really a good environment for them. And so we've tried improving the sound of the device by adding some shims and adding some lubricant, but a lot more work could be done to make it quieter.
And here's our first drawing, and here's the final assembly.
Thank you.